Lesson 7-1, graphing exponential functions. We are on to volume 2, by the way. So new book here, on two. So exponential functions, these are curves that take off real fast. Some common stories you'll see associated with these are things like growth in a bank account that's earning interest, or could be debt, right? If you take out a loan, maybe population growth without resource limitation. There's also an exponential decay. So you see how this is taking off real fast. Here, if I flip a few pages though, here, see how this curve is actually tending towards zero. There's a horizontal asymptote at y equals zero. Uh, there's a common physics application of this, which is carbon dating or radiometric dating. Right, you want to figure out, see if you find an archaeological dig, or there's some artifact that's maybe hundreds or thousands of years old. How do you date exactly? Huh? You can use this carbon dating technique that actually involves this exponential curve. Okay? Now, before I dig too far into the book examples, I do want to clarify something that comes up, especially in my physics classes too, right? Is to distinguish different kinds of curves. So if I say y equals um, x squared, you guys know that's going to be a parabola shape, parabola. Okay? Or if I have y equals x to the power of 3, that'd be a cubic. Okay, so here, if I sketch out real fast, x, y, right? Y equals x squared looks something roughly like that. Okay, y equals x to the third, x, y, that looks something roughly like this. Right? These are not exponential. Exponential is what happens when you reverse the numerical value and um, the variable. Right? So if I have 2 to the power of x, or 3 to the power of x, or eventually what you might eventually see, maybe not today, right, is a special character called e to the power of x. Right? These are what's called exponential. Okay? So if you ever see exponential growth or decay, the variable x is actually in the exponent. That was not the case for parabolas or cubics or polynomials in general, right? But that is true for exponential. Right? And so that's the difference between polynomials and exponentials. Okay? All right. Technological growth can be modeled with exponential growth. Right? A common example is Moore's law. Right? The number of transistors you can economically fit on a computer chip. Right? It'll double periodically. Right? And that's been the case for many decades now. All right, so let's get it here. We got exponential growth, part of exponential function. We got f of x equals b to the x. That's just showing you guys. A lot of these will have these horizontal asymptotes, like here. Which emerges naturally. You can just create a table. That's actually the first thing you do. Say, hey, let's complete this table. Hey, I've always been telling you guys this whole school year, if you're ever not sure what a graph looks like at all, you can make a table and just start plotting points, and the graph naturally emerges. And so we have here, they have a table of values for f of x equals 2 to the x. Now they're telling you exactly what the graph looks like, so you can see it. F of x equals 2 to the power of x. Okay? And then over here, they have a partially completed table. Okay, so here, let's see if we can fill in the rest of this. Okay. So what if I have different x values? They're going from -3 to 3. Yeah, okay, so I'll stick with that. -3, -2, -1, 0, 1, 2, 3. Okay. And then what is f of x? Which we're calling 2 to the x. So here, I'll just rewrite that, 2 to the x. Okay. Okay, well, all I have to do is plug this in the calculator. So it's 2 to the power of, and then in parentheses, -3. Okay. Now, guys, here, maybe I'll write this down on paper too. 2 to the -3 is the same thing as 1 over 2 to the 3, which is 1 over 8. Actually, that should be the answer. And as a decimal, that's 0.125. Yeah, that's exactly what that is. 0.125. Okay. So now we have our first coordinate, where when x is -3, y is 1/8. 1/8. That's pretty small. Right? So that's this coordinate right here. When x is 3 to the left, that's -3. Y is just 1/8 or 0.125. Right? We can do that for all these values. Right? So that this would be 1 over 2 squared, 1 over 2. Yeah, okay, so let's go on. Okay. So yeah, no surprise. This is 1 over 4 or 0.25. If I put -1 in the exponent for x, I get 1 over 2 or zero point 0.5 because 2 to the -1 is 1 over 2. So look at that. Right? Now, what about 0? 0. I bet some of you guys know this. So as a math rule, any non-zero number to the power of 0 is always equal to 1. Right? And that especially makes sense when you look at the the graph, right? I mean, here's the graph right here, so it's merging, right? Like if you plot all these points except that one, you just look at a graph like, oh, okay, well the only thing that would fill in that would have to be one, right? It's like another way to say this, maybe colloquially, is like how many twos do we have? Well, there here if there was like one, two to the power one would be two. Two squared is four. That's two times two. Uh, right, to the power of three, two times two times two, that'd be like eight right here. So if I go like that to the power of three, you get an eight and so on. Right. Right. But how many times do we multiply two by itself? Well, it's zero, right? So as a rule, we say any non-zero number raised to the power of zero is just equal to one. Right. So we get all these coordinates. We got seven coordinates here. The exact same seven coordinates here. So here's negative three comma one eight. Okay. Here's zero comma one. Here's two comma four. Right, so I'm up. Right. Now there's a horizontal asymptote going to the left, right? So this will asymptotically approach zero. There's no asymptote going to the right, right? It just takes off forever real fast, right? So these functions grow way faster than the polynomials we've been working with from first semester, okay? Oh, here, they ask for domain, range, intercepts, asymptotes. Let's go and finish that. Okay, so I could say the domain for what we just did. Okay, should be all real numbers. So I can write set builder notation x such that x is an element of all real numbers. You have to remember that. Okay. Or I could write it as an interval notation from negative infinity to infinity. Okay. So x can be anything. You can plug in anything you want for x and you can get a number back. Okay. Now the range is a different story. The range, well, you see it bottoms out at zero. Now, this will never approach the y value of zero. They can asymptotically approach it. So I could say y such that y is strictly greater than zero, because y can be anything positive. It just can't be negative. Like, could y be positive four? Yeah, it is right here. Could it be negative four? No, it's not going to exist anywhere down there. So there's a range restriction. Okay? And you could use interval notation. You could go zero to infinity. Okay. And notice that I am putting a parenthesis on the zero because it will never actually reach zero. Okay. Um, so let's do y-intercept. Okay. Well, I see it right here, 0, 1. And it's the same thing I showed you guys right here. Here's your y-intercept. It's just where's the graph across the y-axis. That's to say where is x equal to 0. Right? So now this is a coordinate 0, 1. Okay. Uh, keep in mind this is a coordinate. All right, this right here is an interval. At a glance, they look kind of similar, but refer to two totally different ideas. Okay? Okay, ooh, how about asymptote? No, I do say a horizontal asymptote. Okay, and that's at y is equal to 0. Okay? Because if y is equal to 0, and x could be anything, but y is equal to 0. See, I could dash up a horizontal line right here. Right? If you go to the left forever, then this graph will approach that asymptote but never reach it. Right? End behavior. So end behavior. Okay. As x approaches negative infinity, f of x approaches, well, if we go to the left forever, we're approaching 0. Right? But the other way, as x approaches positive infinity, f of x approaches. Now, if you go to the right forever, you go up forever, in fact, really fast. So also positive infinity, infinity. So it goes up and to the right forever. All right, there you go. There's a real basic exponential curve right there. All right, let's go through all the other examples. It's fun. Ooh, they jump straight into transformations. So we got g of x equals negative 1/2 times, and then 3 to the power of x plus 4, and then plus 1. Right. So I'm going to think of this as the parent function. I'll say parent function. I'll call it f of x. Let's just call it 3 to the power of x. Actually, is that what we just did? No, we just did 2 to the power of x, but it's really similar looking curve. Okay? You can kind of see it here in blue, right? And it's going to be the same basic shape as the last example we just did, maybe a little steeper because it's 3 to the power of x. Same basic shape. Okay. But then what from there? Like if this is my parent function, I want to put it through this set of transformations. Right? Well, I know what this negative 4 means right here. It means to go left 4, right? And that's from tagging that plus 4 onto the x. So that's left 4, right? I know it's going to be upside down because this negative in front. Okay. It's also going to vertical. I'm going to say stretch times 1/2, which is really like a vertical shrink, isn't it? Right. So it's just like right, that's what that 1/2 is doing. It's making it like flatter. Right. And then there's this plus 1 over here. So then that would make it go up 1. Okay. And I think that covers all of them. Okay. So if you start with y equals 3 to the x, which again looks pretty similar to the last one we just did, which is this blue curve right here. Okay. Let's put through all those transformations. So left 4. Okay. And you can follow some points and some asymptotes. I know this asymptote I can follow. I know there's this point here at 0, 1, same intercept as before. I could follow that point. You're going to go left 4. That's left 4. I flip the whole thing upside down. Right. Then vertical stretch 1/2, so like smash it, make it like half as tall, sort of, right? And then shift the whole thing up 1. Right? Yeah, I see that horizontal asymptote right there. Right? And I see one of the coordinates looks like, say it's left, say left 4, 2, 3, 4. We go through this again. Right, upside down, stretch half. Right. I think. Yeah, right. I think what used to be the coordinate 0, 1 of the parent function ended up at negative 4 comma 1/2 exactly. Oh, I can throw that in the calculator. I can make sure, right? So I think one of the coordinates is on this g of x. So g of negative 4, I think, uh, should be equal to 1/2. Let's see if that's true. I got all these translations correct. Okay. And so go negative 0.5. I'm just copying this down. Right, times 3 to the power of, and then in parentheses, x plus 4. Now for x, I'm going to plug in negative 4. So negative 4 plus 4. All right, close parentheses. All right, so I think I'm out of all this. And then on the end, I'll tie it on to plus 1. Let's see if I get a half out of that. Yeah, I do. 0.5, that's half. All right, so that's where that point is. All right, so we've got great normal graph translations. This is something we did, of course, last semester. Not quite a bit. So translations, boom, there you go. All right, what's this example 3 here? Identify the value of k and write a function for j of x equals f of x plus k. Okay. I can see it right on this graph. So they gave you this blue f of x. So this looks like, okay, they're saying it's 3.5 to the power of x. Right? So really similar to the last couple examples. It's just uh, a whole number that's bigger than 1 to the power of x. Start off with this basic shape. Okay? And then it looks like you just shifted down too. So I think that j of x, they're saying j of x is f of x, which is 3.5 to the power of x in this case, minus 2, right? Especially that horizontal asymptote that really stands out. It just jumps down 2. So I think that's the answer right there. That's all. Right. Example 4. Use exponential growth functions. Mr. Lopez recently won the lottery. Ooh. Suppose he takes a lump sum payment and okay, let's just call it $50 million. Let's say taxes, that's all been accounted for, blah, blah. Yes, $50 million. What does he want to do with this $50 million? He puts it into an account that yields 5% interest annually. Uh, graph a function that models the amount in his account. Estimate the amount in the account after 20 years. Right, so yeah, what's the power of exponentials as it applies to save money? Okay. Now, as long as now if you want to dig a little bit more into the weeds, what are we talking about 5%? Is this a real or a nominal interest rate? So let's say it's nominal. That means you have to subtract out inflation to say what is he really earning. And if inflation was 5%, then it would be kind of a wash, right? But what if inflation was only like 2% or 3%? Then he would be making a net profit just off the interest, right? How much are you talking about here? Now, here's where there's this model. It says the amount you have as a function of time. And I'm imagining you guys probably saw this in Algebra 1, but this might be a review, hopefully, equals the principal amount. Now, I think it was lowercase a. I usually see this as P for principal. I don't know, maybe it depends on the textbook you have, right? And then 1 plus the interest rate to the power of the amount of time that's passed. Okay? And there's different variations on this. So this is just simple interest. Maybe you're just compounding at the end of every year, right? And maybe later on this class or possibly in Algebra 1, you saw where maybe there's like quarterly compounding or continuous compounding, or that this is even simpler than that, right? Right. So what would this model look like? So I can say the amount that he has in his account after time is equal to, now in the place of principal, because P is principal, right? It's the amount that you start with, right? And this R is the interest rate, and this T could represent the amount of time passed. Okay. This will be in years. We'll just say at the end of every year, you know, they apply the interest rate. Okay. Right, so in place of the principal, we're going to put $50 million. I'll just spell out the word million. Right? You could tag 6 zeros onto that. You guys get the idea. $50 million. Cha-ching. And then one plus the interest rate. Well, the interest rate, remember, was 5%. Guys, percent as a decimal. Isn't that here? I write it down here. 5% is the same thing as 0.05, right? As in 5 over 100. That's what percent is, per percent, literally per 100. Okay? So 1 plus 0.05, isn't that 1.05? Okay. And then t could be, here, I'll leave it generic for now. It could be any amount of time. Okay. Do you guys see how when you do 1 plus the interest rate, it comes out to a number a little bit bigger than 1. Okay, this means this money is going to slowly grow. So if you earn 5% interest for just a year or two, okay, maybe you made a little bit of money, but probably nothing to get super excited about. But what happens when you extrapolate out to like 20 years? Right now, this is going to get crazy, but well, you guys will see. Right? See the numbers for yourself. So let's do the amount after 20 years. 20 years of this. Right? Here, I'll throw in the middle. What about after 0 years? Let's do after 1 year. We'll do both of those just so I can show you guys. Okay. And so what if 0 years have passed? So we're not compounding this at all. Well, logically, he just put $50 million in the bank, so you should have $50 million. I'm just going to type the number 50, and I'll say the word million after that. Okay. So I say times 1.05 to the power of zero, because we're going to have compounded those 0 times. He's earned interest for like zero amount of time. Oh, he has all $50 million. And that's kind of what I was telling you guys before, where for these exponential functions, like f of 0 is equal to 1, like anything to the power of 0 is equal to 1, then if you multiply that by the initial $50 million, you'd have $50 million. Cha-ching. Right? What about after 1 year? Okay. So I think logically he should have earned maybe 5% beyond that. So it should be the principal plus 5%. Yeah, look at that. A 5% of 50 million would be 2.5 million. So now he's up to $52.5 million. Right. As long as he doesn't touch the money or take any out. Maybe he has a like a long-term account. All right. So it looks like I wanted to do a couple of small examples with the guys to say, yeah, okay, I can see that after 0 years, 1 year, that makes logical sense that would have to be the outcome. Right? That's a nice thing about math too, right? Hopefully it makes sense why this equation looks like this. Now you can snap this together. But if you weren't sure, like, wait, did I put that together correctly? You can run a couple of little small examples after 0 1 years and say, okay, yeah, that is consistent with what seems like should be true, right? So now we're going to take this all the way out to 20 years. So not 0 years, not 1 year. Let's go all the way out to 20. How much? Here, maybe take a guess before I hit enter. How much money do you think after 20 years in this account, 20 years compounding at 5%? The answer is $133.66 million. Ching ching. Yeah, $100 million. Right? So, and you see, rough rule of thumb, he's earning over $2 million a year just off the interest. So, as long as he doesn't go crazy, as long as he doesn't spend, like more than $2 million a year, he's just living off the interest. Pretty good, right? Pretty good. All right, okay, check. All right. Graphing exponential decay functions. Exponential decay. Right. That was what this physics poster had for you guys was radiometric dating, carbon dating. You can also do this with uranium and lead for even older rocks. What does your book say? Occurs when the initial amount decreases by the same percent over a period of time. We're talking about percent changes. So for exponential function, f of x equals b to the x, b is between 0 and 1. Well, here, I might say it like this. There's two ways you can talk about exponential decay. Okay? You can say that the amount you have as a function of time, let's go as a function of time. Right? It's common to do. Okay? Could be maybe the amount that you start with uh, times some base number. What did your book use? They used B for base number. Okay. Now, if the base number is between, if B is between, uh, let's say one and infinity. Well, let's just say it's bigger than one, right? Right. Then it has to be a negative exponent, right? Okay. Or you can have the amount as a function of time equals the initial amount times b to the t, where b is less than one. Okay. Well, let's say between 0 and 1, I should say. Okay. So, like, for example, if b was a half, then every time interval you're multiplying by half and half and half. So if you started out with 8 of something, you got half of that, now you're down to 4. Half of that, now you're down to 2. Half of that, now you're down to 1. Half of that, now okay, so you keep multiplying by a half, it could be. Okay. That could be all exponential decay. Okay. Okay, and then they go through some examples here. Okay, so examples, counterexamples. What's growth or decay? Example 5. Well, let's list them all out. F of x equals 5 to the x. We got g of x is 2 over 7 to the x. H of x, 4/3 to the x. J of x, we got 1.05 to the 1.05 to the x. Isn't that what we just did with Mr. Lopez and his lottery winnings? I think that's the same thing. All right, and then k of x is 0.85 to the x. Right. Um, right. Yeah, so this is growth and decay and by how much? Right. So this would be, these are all exponential. Exponential. Right. Again, notice for every single one of these, there's some base number and it's raised to the power of x, which I don't think you guys saw last semester at all, right? But you're seeing it now. Okay. So these are all exponential. This first one would be growth. Okay. And it's a growth by 500%, because 5 is that, well, 500% is 5, because if I take 500%, percent is 5 by 100, that's the same thing, right? 500. Okay. So if you start off with one of something and then you go one interval in the future, right? Okay. Now you're up to like 5 times that. Okay. So here, if I made a little table, what's 5 to the 0? 5 to the 0 is 1. Okay, so we start off with one of something at time 0. Then after one maybe interval of time, now we're up to 5 that thing. After 2 intervals, now we're up to 25. Okay, so you keep multiplying by 5, right? So it'd be a 500% growth. Now, 2 over 7, isn't that between 0 and 1? So if you take 2 over 7 and, well, let's just put it to the power 0. Okay, so we start off with maybe 1 unit of something, whatever. Okay? But then the power 1, 0.28 something. Maybe we have 28% of what we started with. Well, if we let 2 iterations go by, now we're down to 8% of the original amount. See how it's getting less and less and less? And I knew that was going to happen because 2/7 is between 0 and 1. So this would be decay. Right? How about the rest of these? 4/3. Well, 4/3 is 1.33. So this would be exponential growth. Okay. Actually, here if you just divide this out 4 over 3, okay, you can call this 133%, or you can say it's growing by 33%. Here, I'll put that in parentheses. Okay, growing by 33% per interval, maybe interval of time or whatever the x-axis represents. Okay. This next one is also growth. Same thing as Mr. Lopez and his lottery winnings. Maybe invest in whatever account he has, whether it's like index funds or certificate of deposit, whatever it's doing. It's earning 5% interest per year times however many years. Okay. I say growing by 5% per interval. In the example we did a few minutes ago, every interval represented 1 year, so 5% per year. Okay. 0.85. Well, that's less than 1, so this would be decay. Okay. Actually, 0.85, isn't that like losing 15%? If you put in the equation we were working with before, the amount you have after some time is equal to the initial amount times 1 plus r to something. Okay, and it's real basic curve here. Now, if this 1 plus r is less than 1, then there's going to be a decay. So I think this r would be negative 0.15, wouldn't it? Okay. Which leads to what I'm trying to get at here is that your I would say shrinking by 15% per interval, per interval of time, maybe every year or something like that. Okay. Okay. All right. Um, Math History Minute. Mathematical biologist Treshette Jackson uses many different approaches, including continuous and discrete mathematical models. Okay? So continuous is like these smooth curves. Discrete is like maybe you do iterations like minute by minute or hour by hour, or something like that. Numerical simulations and experiments to study tumor growth. In 2003, she won the Sloan Fellow in Mathematics Award. Yeah, all right, so yeah, mathematical biologist. Yeah. Okay, so if you ever work with, say, like bacteria in a petri dish, a lot of times these bacterial population models will start off exponential growth, right? Like but I guess any one of these, right? Right. Now, in a petri dish, there would be limiting resources, so they'll eventually turn to logistics curve, and maybe the population levels off. But usually, it starts off looking like this. If you have a really big dish, right, then maybe you can sustain that a little bit longer. All right, but what's this example here? Oh, we got graph f of x equals 1/2 to the power of x. Find the domain, range, intercepts, asymptotes, and behavior. Well, we did this before for a different example, right? And they give you the whole example right here. So I'll just do this on my calculator and show you guys that it matches with the table and the graph that they're already giving you. Okay? So if I have 1/2 to the power of x, right? Well, let's move that, right? I guess we're going starting at -3 and going to 3. Okay? So 8. So when you plug in -3 for x, you get 8 for f of x. Exactly what my calculator says, exactly what the table says. Okay. Let's do these other values. So -2, we get 4, boink. -1. -1, all you're doing is you're just taking the reciprocal. 1/2 reciprocal of that is 2, right there. Anything to the power of 0, 0 is 1. Right, you guys seen that a few times? Boink, right there. Okay. The example you guys saw on the compounding money interest is that if you make an initial deposit and there's been 0 time that's passed to accumulate any interest, then you have 1 unit of exactly what you started with. Yeah. Right. If you plug in 1 here, of course you get 1/2. 1/2 to the power 1 is 1/2. Right. 1/2 squared. Ooh, that's 1/2 times a half. Well, that would be a quarter. Right? And then the power of 3, you get 1/8, boom, right? Right. Then if you plot all these points, so 0, 1 is point 3, 1/8, -3, 8, right? And right, line them all up. Okay. Looks like the domain, just like before, could be -infinity to positive infinity, all real numbers. Now the range, same range restrictions before. You can start at 0, not including 0, and anything above that, anything greater than 0, strictly greater than 0. Okay. But notice that there's no y values down here in negative territory. Okay. Okay, I see this y-intercept at 0, 1. I see a horizontal asymptote at y equals 0. Right? Really, really similar to the example that we did near the beginning. Right? Right. And then example 7, graph transformations of exponential decay. Transformations. So example 7, given us g of x is -2, and then 1/4, and then x minus 4, and the whole thing is +3. Right? Well, there is this blue f of x function, which, oh, here it is the parent function. So f of x is just 1/4 to the power of x. Okay? So this is the parent function. Right, there's your parent function right there. Right. Okay. Notice that 1/4, of course, is between 0 and 1. So you keep multiplying by a quarter, you get smaller and smaller and smaller, and it asymptotically approaches 0. Right. So hence this blue curve right here. Right. Okay. Now, starting from that parent function, I see this looks kind of like that, right? It's got the 1/4 base, it's got a power of x, that stuff, right? I see some shifts. This -4 here means to go to the right 4. This -2 means upside down, and also vertical stretch. times 2, right? So we're going to stretch it out twice as much vertically. Okay. And this plus 3 tagged on the end means up 3. Right? So that should be all the transformations. Right? So if you started with this blue curve, okay, so we got if you plug in 0, you get 1/4 to the 0 is 1. That's the 0.01, right? And then everything else follows. Okay, so I'm gonna take this to the right 4. So right 4, 1, 2, 3, 4. Okay. I'm gonna shift the whole thing upside down, okay, which should make it look like this. Then vertical stretch by 2. Right, so make it like twice as tall. All right. All right, and then the whole thing. Um, okay. Okay. Up 3. Okay. Yeah. All right. So I think one of my points would be g of 4. If I follow that, okay, right 4 upside down times 2 up 3. I think it should be 1. Okay. Um, no, let's see if that actually works. Okay. And of course, you can make a whole table of values. You could plug in a bunch of x values if you want. I'm just going to plug in 4 here and see what happens. So -2. So that's great. All right. Times and then 1/4 to the power of, and then x minus 4. Well, I'm going to plug in 4 for x, so it'll be 4 minus 4. Right. And then close parenthesis, and then be plus 3. Let's see if I get 1 out of this. Yeah, 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 yeah. All right, so at least that's that one point that follows around. This asymptote also follows. You see the asymptote shifted up there. You can make a whole table of values. Okay. There's your transformations, all the transformations. And of course, they're showing you the answer. It's the correct answer. Same thing I got. All right. All right, highlighted some of these ahead of time. Let's take a look. Graph each function, find the domain, range, intercepts, asymptotes, and behavior. Okay. So number 1, got f of x equals 3 to the x. Okay. Okay, so if you ever weren't sure, you could always, of course, make a table of values here, x and f of x. Let's go -2, -1, 0, 1, 2, 3. Did that. Okay. Well, f of x, f of -2, that's 3 to the -2, which is 1 over 3 to the 2. 1 over 3 squared, that's 1 over 9, or 0.111. -1, that's 3 to the -1, which is 1 over 3, or 0.333. 0, any non-zero number to the power of 0 is 1. Okay. 3 to the 1 is 3. 3 squared is 9. And 3 to the 3, that's 3 times 3 times 3, is 27. Okay. So let's throw this on a set of axes. See if it's x-axis, y-axis. Okay. -2, -1, 0, 1, 2, 3. Okay. I'm going to squish the vertical axis because I got to get to 27. So let's go 10, 20, 30. 10, 20, 30. All right, let's plot all these points. So when x was -2, y was 1/9. So that's real tiny. So about right there. Okay. When x was -1, about 1/3. A little higher, but kind of hard to tell again. Okay. 0, 1. Okay. If this is about 1/10 of the way up, it's probably right about there. 1, comma 3, 2, comma 9, 3, comma 27 is way probably about here-ish. Yeah, look at all those points. Look at that nice, ooh, smooth curve going on there. Okay. Okay. So they ask for a bunch of details here. Break open a new paper, but they want domain, range, intercepts, asymptote. Right. So domain. Okay. In interval notation, let's say x such that x is an element of all real numbers, or you go -infinity to infinity in interval notation. Now the range, we got y such that y, now here there is a restriction, right, because y can only be positive. So it's strictly greater than 0. Or you could write that as 0 to infinity in the using interval notation. Okay? What you're probably definitely catching on to by now is that a lot of these exponential curves have really similar looking domain and ranges. Okay? Domain is usually you can plug in anything, And the range is usually restricted to, brushes right up against that horizontal asymptote. Um, y-intercept is that it should be right here, 0, comma 1. Okay. So for your parent functions, for these exponential functions, that's usually universal y-intercept. And then asymptote. Well, there's a horizontal asymptote. There's no vertical asymptote here, but there's a horizontal asymptote. So maybe I'll specify that. Horizontal asymptote at y is equal to 0. Okay, so this graph will never reach y equals 0, but it'll asymptotically approach it if you go to the left. Then that brings us to end behavior, okay, which is that as x approaches negative infinity, if you're going all the way to the left, y, or f of x, if you like, approaches 0. Okay? As x approaches positive infinity, if you're going all the way to the right, then the y values, f of x or y, also approaches infinity, goes up forever. I think that knocks out all those. All right, how about number 2, y equals 5 to the x. So number 2, y equals 5 to the x. Okay. Well, it's going to be really similar, isn't it? Really similar. So let's do a table here, x, y. So -2, -1, 0, 1, 2, 3. Okay. So 5 to the -2, that's 1 over 5 squared, 1 over 25. -1, 5 to the -1 is 1 over 5. 5 to the 0 is 1. 5 to the 1 is 5. 5 squared is 25. 5 by 5 by 5 is 125. Okay. All right, then let's go 1, 2, 3. -2, -1, 0, 1, 2, 3. X, Y. All right, well, we're going up to 125. It's pretty crazy. Maybe I'll just cut that last one off. Let's just go 10, 20, 5, 10, 15, 20, 25. Should get a good representation. So -2, 1 over 25. Ooh, here 1, 1 over 5, 0, 1, 1, 5, 2, 25. Okay. And then, well, if I did include this last point, 3, 125, 3, that'd be like 5 of these 25s. Okay, it'd be like off my desk up that way. See how fast these are taking off? Yeah. So you want to be careful with interest rates, right? Right. So yeah, if you're on the debt side of interest rates, then your debt balloon's huge. Right? If you're on the growth side of interest rates, like uh, who was it before? Mr. Lopez was winning the lottery. Well, that'll take off real fast too. That's what exponential curves are. Okay, and okay, this has really similar features to what we were just looking at over here. Okay, so I don't think it'd be too different from all these, would it? Right. Graph each function. Ooh, so number 9. Get a little space up here for a parent function because we're looking at f of x equals -0.4 times 3 to the x plus 2, and then plus 4. Okay. Well, I think my parent function, maybe I call it p of x for a parent function, should just be plain 3 to the x, right? Which is one we did not too long ago. Here's 3 to the x. So I'm going to use this right here as the parent function. Okay? Now, relative to this goes upside down, then vertical stretch times, well, 0.4, that's 2 this, isn't it? Right, if you want to think it that way. Okay. This right here means go to the left 2. This right here means go up 4. Right? No draw left. Okay. Um, you know what? Okay, here's this. I'll plug some points into a table, and then I'm just going to put this one in Desmos so you can see. Right, so you can see how I'm getting all these table values and also what looks like in Desmos. Okay. So -0.4. Okay. Then we're doing 3 to the power of x plus 2. Here, I'm going to do this little tricky example. Here. I'm going to do answer plus 2, and I'll just go plug in different values for answer. Okay. Close, close, and then you got a plus 4 type on the end. Okay. Let's go to -2, -1, 0, 1, 2, 3, see what happens. Okay. And so the first answer is John. Don't worry about that. Okay. So I type -2, then I plug that in. Get 3.6. -1, 2.8. 0.4. Okay. Now should that make sense? Um, Actually, here, if I plug in -2, this comes out to zeros. This whole thing's 1. That would be, yeah, it would be 3.6. Yeah, that's true. If I plug in 1, I'm getting -6.8. If I plug in 2, I'm getting -28.4. And 3, I'm getting -93.2. Right? Yeah, see how it's racing off, it's taking off real fast, right? Going in the negative direction, and it's that's this upside down part of the exponential curve. So it's exponential growth, but it's just upside down, right? And then it looks like this is asymptotically approaching. Uh, should be yeah, because if this came out to what would happen if I plug in a big negative number for x? Like what if I plug in -100 for x? Can you do that? Yeah, this will asymptotically approach 4. I'm looking at the horizontal asymptote right here. All right. All right, let's see what Desmos has to say about that. Do that right here. And yeah, look at that. See, going to the left, it asymptotically approaches y equals 4. Okay. We got this y-intercept right here at 0.4. Okay. Just like I showed you on the table. Right. And then now it's exponential growth, but upside down. So it takes off real fast going down to the right. There you go. It's all there. All there. We just did. All checks out. Yep. All right. We are good. Um, I identify the value k. Okay. So we're doing some real basic graph translations on problem 13. So I choose both of them. Okay. It looks like g of x is f of x, but shifted up 2. I think that's the entire thing. And then 13, it looks like this g of x is f of x, but flipped over the x-axis. So it's upside down. So it's just negative f of x. Okay. I think that's, boom, just did 2 right there. That's it. Okay, number 14. Subscriptions to an online arts and crafts club have been increasing 20% every year. Uh, the club began with 40 members, writing graph a function to represent the number of subscribers over the first 5 years. How many subscribers were there in year 4? Okay. This reminds me a lot of the amount after some time is equal to the initial amount times, or you call it the principal. Okay. 1 plus the rate of growth to the number of iterations. Maybe year by year, I'll call it x. So maybe x is 1 year, like that. And if we're growing by 20%, this r equals 0.20. The initial number of members was 40 members. Okay. Okay, and x could be any number of years that have passed, well, I guess up to 5 years. Okay. So the number of members, it's dp for population if you like, right, is 40. We start with 40 times. Now 1 plus zero point 0.2, well, that would be 1.2. Or you could say 6/5 if you like. Right? Okay, I think that's what we're modeling right there. Right? This is the mathematical model for this whole paragraph. It's the same thing. Right, now, how about after year 4? And then they want us to graph this. Right, so okay, let's figure out year 4. I guess put a 4 where that x goes. So 40 times 1.2 to the 4, right? Well, I'm going to round to the nearest whole value because we're talking about number of people, right? Right. So I'll call it about 83. Here, we can do a whole table. Do a whole table. Right. So let's do x is the number of years that have passed, and well, I used a, so let's just use a. Okay. I don't know, like t here. Sorry, I should be consistent with my variables here. Right? I was thinking t in terms of time, and then I swapped it to x for some reason. So let's just keep it all x. Why not? Okay. Right. So let's go year 0, 1, 2, 3, 4, 5. Okay. So I'm going to plug each of these years into x and see what happens. Okay. Well, I know if I plug in 0, what's going to happen. This whole thing becomes 1, and I just get 40. Okay. Let me show you guys that that's true. If I plug in 0, yep. So we start off with 40 numbers. At time 0, the club started with 40 numbers. Okay. Now, after 1 year, it's grown by 20%. 20% of 4 is 8. If you add that to the original number, you get 48, right? Or the calculator just does it all. Okay, 48. Okay. Let's let 2 years of growth go by. 57.6, I'm going to say approximately 58. Okay. 3 years of growth, um, approximately 69. 4 years of growth, approximately 83. Oh, that's what we got before. Okay. Right, and so that's that. Same thing. And then 5 years of growth. They say this model could represent the 5 years. Okay. Approximately 99.53, I'll call it 100. So about 100 numbers after 5 years. Okay. Now, could this grow forever? Well, we're on a finite planet, and if you had all 8 billion people interested in arts and crafts, I mean, at some point, there's only so many people on the planet, right? But maybe this could represent, this equation could model the first few years. Yeah, okay? I mean, you could graph all these points. Here, I'll make a rough sketch over here, and then I'll flip over to Desmos and say what does Desmos have to say about this. Okay. So we're looking at the number of people after some X number of years. Let's go 1, 2, 3, 4. So 0, 1, 2, 3, 4, 5 years. Okay. Now I know this club is going to go up to 100 people, so I need to scale this. Let's go 20, 40, 60, 80, 100. 20, 40, 60, 80, 100. Okay. Right, and then I get to plot those points. So at time 0 or year 0, there were 40 numbers. So 40 numbers started. After 1 year, now we're up to 48. Well, here's 50, so 48 is a little short of that. After 2, 58. Ooh. After 3, 69. 4 is 83. 5, about 100. Yeah, you can see it here. See, it's kind of curving up, isn't it? It's slowly growing. Okay. That is an exponential curve. Now, you might say, oh, that looks kind of like a parabola, but it's not. This is totally not a parabola at all. Okay. Actually, this will grow way faster than the parabola. If you put any parabola next to this, then you let enough years go by, and eventually this exponential curve is going to beat that parabola because it grows so fast. All right, so let's plug this into Desmos. See what does Desmos say. All right, so plug that into Desmos. Let's see, that's that. That's that. Yeah. Okay. Now, Desmos gives you like before the club started to like if that was part of it. But what's relevant to us is starting from 0 to 5. Well, okay. I think I can change these axes too. We're really just looking at this part here, right? And at 5 years, just go up to about 100. Yeah, like that's pretty close to 500 right there. Yeah, that's it. That is it. Yeah, throw in a little bonus here. So if you click this wrench, you can change the axis settings, right? Because right now it's okay. Here, like maybe I only want this x-axis to go from like -1 to 5. Maybe that's what I want. Let's try that. Okay. And then yeah, see how okay, that looks a lot cleaner to work with. Here it is, right? So we're going from year 0 to year 5, which is like right there. Boink. Right, it went up to 100. Okay, so same thing. There you go. All right, next. Money. Sunil opens a savings account with compounds interest rate of 3% annually. Let P be the initial amount he deposited. P usually stands for principal in this case, and T is the number of years it's been open. Write an equation to represent the money in his account and estimate after 10 years. Okay, and then how much time would it take to double in value? Okay, so I'll try that. So 16. So the amount he has after some time is equal to the P principal, and then 1 plus the interest rate, and then the number of years that pass. We're doing just real simple compounding at the end of every year. Okay. So the amount he has after some time, Well, you put in $500. That there's this principal, $500. Okay, he makes no deposits or withdrawals. Okay. And then after 10 years, at a what interest rate? 3%. So so this is like 1.03, you could call it. And then take there. So the amount after 10 years would be $500. Okay. And then 1.03 to the power of 10. Okay. So we're multiplying by 1.03. That would be at the end of the first year. Then that gets compounded times another 1.03, another 1.03. Right. You do that 10 times. 500 times 1.03. I could keep multiplying. Here's another way to say this times 1.03 times 1.03. Okay, I'm going to delete all that out. Just going to do that 10 times. So that would be $671.96 according to this. Okay. So 3% growth is not as much as we were looking at the earlier example, and also 10 years is not 20 years. Okay, so smaller interest rate for less time. The growth may not be quite as much. All right. How much time would it take to double? Well, I know what double would be. That would be looking for $1,000. Looking for $1,000. Okay. If we started with 500 and then times 1.03 to the power of t. Well, now we're solving for t. You know what? It says estimate. The way to do this properly mathematically is to use logarithms, which we're going to eventually do in this class, but show you how it is. So divide those sides by 500, 500, 500. Okay, so you got 2, factor of 2, 1.03 to the t. Okay. Now, you could sit here and guess and check. Right? You could just plug in a bunch of different time values until this comes out really close to 2. You could totally do that. Okay. I'm going to use a property called logarithms. So here I'll use natural log. Natural log 2 equals natural log of 1.03 to the power of t. And what's nice about logarithms is that if you have some power like this, you can bring this down in front. So it's no longer a power, and then you can actually solve for it. So natural log 2 equals t we're solving for times natural log of 1.03. Okay. Then divide both sides by natural log 1.03. So the time would be, let's get an exact answer on this. So natural log 1.0, no, it's 2 divided by natural log 1.03. Looking at about 23.4 years. Okay, so now if it's only being compounded at the end of every year, that'd be 24 years, wouldn't it? Because you'd have to wait for the last year. So the answer, it'd probably look for 24 years. So if I take 24 years and I plug it back into the original statement, then it should give me about $1,000 because 500 times 1.03 to the power of 24 years. Let's see if this dumps a little over $1,000. It sure does, 1,000 and change. Okay. Time. Okay. Yeah, let's do a few more here with you guys. Um, all right. These two we can knock out real fast are these exponential growth or exponential decay. So looking at g of x is 0.99 to the power of x. That's decay. Right? And we're losing or shrinking 1% per interval. Could be every year or however much time. Okay? For because 99% is 1% less than 100%. For number 20, j of x is 5 over 4 to the power of x. Okay? Well, it'd be growth. Okay? Now, 5 over 4, I know is 1.25, or you could say 125%. Okay? So we're growing by, well, okay. See, if this was equal to 1, there would be no change at all. So you have to subtract 1 or subtract 100% from the percentage if you like to say how much is actually growing by. And it's growing by 25% per interval because you're always multiplying by 25% above the base value. 25, graph each function, describe everything that, okay. Here, I'll just plug this into Desmos. And you can see, so f of x is 1/2 to the power of x. We get a brand new Desmos up there. Desmos. Whoop. Hang on. Get this back. Get this back. Okay. Graphing calculator. All right, let's do f of x equals 1/2 to the power of x. All right, whoops. 1/2 to the power x. There we go. That looks better. Okay. Yeah, see how that's exponential decay? So we start, if you plug in 0, anything to the power is going to be 1, 0, 1. Right? And then above that, after one interval of time, now we're down to a half. After two intervals, half times a half is a quarter, then an eighth, then 1/16, then 1 over 32. See, it'll asymptotically approach 0 to the right. So there you go. Okay. The domain could be from negative infinity to infinity. You go left and right as far as you want. But the range, well, there is a range restriction. Range y can be strictly greater than 0, but not less than 0. Yeah. It's all there for you. And uh, let's do, we got a couple here. Compound undergoes exponential decay. Already I'm thinking sort of like this, right? Like that. With initial amount 27.3 grams, the amount compounded decreases by 10% each year. And let's model that. Yeah, we can do that. So I'll say the amount after some time is equal to the initial amount times 1 plus the rate to however much time. Right. Now, in this case, the initial amount was 27.3, that's grams of whatever, times. Okay. Now, if we're losing 10%, we're decreasing by 10% per year, then the interest rate is negative 0.10, right, as a decimal. Right? Or you could write that maybe more elegantly as 0.9. Or 7.3 is grams, and then 0, so multiply by 0.9 to the power t. Okay. So if no time has passed at all, 0.9 to the 0 would be 1. So, okay, you have what you started with. I started with 27 grams. I still have 27 grams. Okay. If you allow 1 unit of time to go by, it looks like every year. Okay. So you allow 1 year to go by. Well, now you only have 0.9. That's 90%. So 90% of whatever you started with, now you only have 90% of what you started with. See how you lost 10%? Yeah. Okay. And last one, 45. A population of bacteria grows exponentially with initial population at 20,000. After one day, it's up to 30,000. Write a model to explain it. Okay, and then what's going on with the context, right? So yeah, we can do all this. Right? So same basic model. So the population after some time is equal to the initial population multiplied by 1 plus the growth rate to how much time. Now is this okay, we're going day by day. So T represents however many days. Ooh. Now they didn't tell us the growth rate, but I think we can figure this out because they told us that after one day, we're up to 30,000. Right, and that starts from 20,000. So this would all be taking the place of this basically. Right? 20,000 is like this. Okay? And then times 1 plus r, which we don't know yet. But t is one day. Right? So one day goes in for t. Right? Right. So okay, so this is a specific coordinate that we can use to figure out what did the growth rate have to be for this exactly to play out. Right? And then we can figure out the population of this bacteria on any day. Right? Let's figure that. So I'm going to divide both sides by 20,000. 20,000. 28,000. Right? Now over here, 3 over 2, that's like 1.5. So this is like 1.5 equals, and then 1 plus the growth rate to the power of 1 for one day. Right? Okay, so I have 1.5 equals 1 plus r. Subtract 1 from both sides. Minus 1. Okay. R equals 0.5 or 50%. Okay, you got it. So it looks like it's growing by 50% every day. Ooh, right, so per day. Okay. All right, so put it all back together. The population as a function of time is equal to the initial 20,000 times, this is like 20,000 bacteria. Okay. Now 1 plus r, well now I know what r is. R is 0.5, so 1 plus r would be 1.5. And then t is however many days it passed. Okay. I'm going to do one last check. I'll make sure that if I plug in 1 day here, I get 30,000. Right. And then once that works, then we'll know we're definitely good. So take the 20,000 initial number times 125 to the power one. Yeah, get 30,000 out of that. Right. So we are good. And that is 7-1.